Okay, in this video I want to give a geometric interpretation of the determinant. It's actually an interpretation of the absolute value of the determinant. So remember that if you have an n by n matrix, any n by n matrix has a number associated with it. It's called the determinant. And the determinant is a real number if your matrix is a matrix with real entries, which is what we're talking about. It has a determinant, and this determinant is a number, and so it has an absolute value. So we'll interpret the absolute value of the determinant of A. And the theorem is the following. If S is a region, okay, I'm only going to state this in R2 for now. If S is a region in R2 with finite area, then the area, okay, well, first of all, if I have a n by n matrix A, I have an associated linear transformation T sub A, right? So let's call that T. Then the area of T of S is equal to the absolute value of the determinant of A. So this is T sub A is my transformation. Absolute value of the determinant of A times the area of S. Okay, so the area of S is a number. I multiply by the absolute value of the determinant of A. I get the area of the image of S under the transformation. Okay. So that's in R2. There is a similar statement in R3, which is, this involves volume. If S is a region in R3 with finite volume, then the same thing happens. Then when I look at the image of S under the linear transformation, not area, it's volume, of T sub A of S is equal to the magnitude of the determinant of A times the volume of S. Okay. Let's just look at some examples. For instance, let's say that A is this matrix. Well, let's just take a very simple example, the identity matrix. So the identity matrix takes R2 to R2, and it's going to keep everything the same, right? It takes X to X, and so it's going to take the blob to the same blob. It's going to take some region S to the same region S. I didn't give a precise definition. These are supposed to be the same. Oh, maybe I'll actually just literally make a copy of this, just to emphasize that. There we go. Right. The area of S is the same as the area of T sub A of S. S is the same as T sub A of S in this case, and so they have the same area. And the determinant of A is 1. So as expected by the theorem, the area does not change. And it's also true if you change A to be a different matrix with determinant 1. Well, in this case, your T sub A of S will not be the same as S. But it turns out that you're not sort of deforming your region by making it a bigger or smaller region. It has the same area. Okay, let's say that you had the matrix A equals 1/2, 0, 0, 2. So again, this is a matrix with determinant 1. The absolute value of determinant of A is 1. So the theorem says that if you look at R2 and look at the outputs and you look at a region in R2 with finite area, the area of the image will be the same. So let's take a look at, say, this 1 by 1 unit square. Okay. Where is T sub A going to take this 1 by 1 unit square? Well, it's going to take 0, 0 to 0, 0. And it's going to take 1, 0 to where? 1/2, 0. Right? And we'll go to 1/2, 0. And where will 0, 1 go? It will go to 0, 2. And this last vertex, 1, 1, is going to go to 1/2, 2. And we know that this line segment, these line segments, are going to go to the corresponding line segments joining the vertices. That's a general fact about linear transformations. And the inside of this square is going to go to the inside of this rectangle. And so the image is going to be this. So if that's your S, this is your T sub A of S. And if you look at the area of S is 1, and the area of T sub AS is 1/2 times 2, which is 1. And notice what happens when you take not just this unit square, but you imagine tessellating all of R2 with these squares. So you imagine all these unit length squares and plugging them into your, so this is like a grid, and you imagine taking all these squares and plugging them in. Well, this square, for instance, is going to go to this rectangle above. Right? All these squares are going to go to rectangles of dimensions 1/2 and 2, and so these the area gets preserved. And you can even look at different shapes, not just squares. So for instance, let's say that you have the matrix 2, 0, 0, 3. So this is going to stretch the x-axis by a factor of 2 and the y-axis by a factor of 3. And let's say you take the unit circle. So you take this region inside the circle. Let's call that S. So S is all x and y such that x squared plus y squared is less than or equal to 1. And you look at where S goes under the transformation T sub A. Well, what's going to happen is that the point 1 sub 0 is going to go to 2 sub 0, and the point 0, comma 1 is going to go to 0, comma 3. This 2 is a little too far away. Maybe here. And if you imagine plugging in all the points, okay, you're going to get this ellipse like this. And the area of the unit circle we know is pi. The area of this ellipse is going to be, well, the determinant is 6. The determinant of A is 6. And so the area of this ellipse is going to be 6 pi. And that actually matches the formula if you have the ellipse centered at the origin and the x value is A and the y value is B, then the general formula for the area of the ellipse is pi times AB. So in this example, you had positive determinant in all these examples, but it's also true if you have negative determinants, just take the absolute value. Okay. So one way to interpret the absolute value of the determinant of A is it's a scaling factor. And we can also apply this to areas of parallelograms, because what happens is, so let's say you have this matrix A, which is 1, 2, -1, 3. Well, what is A going to do to the unit square? It's going to take E1, 1, 0, to 1, 2. So that's this. And it's going to take 0, 1 to the second column, -1, 3. And so this square, this square is going to go to the parallelogram that's generated by these two vectors. So you imagine forming this parallelogram like this. This square, okay, let's call that S. The image is going to be this parallelogram. Let's call that's T sub A of S, the image of the unit square. And the theorem says that the parallelogram that I just colored is going to have area what? Well, if you take the determinant of A, you get 3 another positive determinant. Okay, well, the determinant of A is going to be 5. It's 3 minus -2. And so, well, this had area 1, and so therefore the area of this is going to be 5 times 1. And so we have another way of thinking about the absolute value of the determinant. It tells you the area of the parallelogram that's where the edges, these vectors, are the columns of A. So you can think of the absolute value of the determinant of A if n is 2, if you have a 2 by 2 matrix, you can think of this as an actual area, or you can think of it as an area scaling factor of the linear map that's described by the matrix. And in R3, the analog of the parallelogram is something called a parallelepiped. So it's like a box, except, instead of the edges being rectangles, you have parallelograms. Okay, and maybe I'll just give an indication of why this theorem is true. This isn't, a rigorous proof. The problem with the fact that this isn't a rigorous proof is that we don't even have a rigorous definition of region, right? I didn't actually say what exactly constitutes a region, and so this theorem is not very precisely stated, but you get the idea. And basically the idea of why this is true is because of the defining properties of the determinant. So recall that the determinant has these properties that if you swap two rows, you don't change the determinant. Well, if you don't change the determinant, you don't change the absolute value of the determinant, right? And the volume also has these properties that if you think of the area of the parallelogram, if you swap the order of the rows, or you swap the order of the columns, the area will stay the same. Okay, you might want to draw a picture to convince yourself of that. If you swap the order of these two rows of this matrix, the volume, the area doesn't change. And also if you stretch A by a certain factor, let's say you multiply A by 2, so you're going to get 2, negative 2, 4, 6. What happens to the determinant? It gets multiplied by 4, right? Because it's 2 squared. So the absolute value gets multiplied by 4. And what happens to the volume? Well, in this case, the area. Well, in this case, if I look at 2a and I look at the image of the unit square, I'm actually going to get 2, 4 and negative 2, 6. And so what happens to the area? It also gets, okay, I have 4 parallelograms of equal area. The area also gets multiplied by 4. So the absolute value of the determinant behaves a lot like the volume in those two aspects. And when you look at the other row operation, this other defining property of the determinant, when you replace one row by that row minus or plus the multiple of a different row, the determinant doesn't change. So the absolute value of the determinant doesn't change. And it turns out that if you want your volume, whatever property area and volume has, it also has this property. Okay, so I'll let you think about why that makes sense. When you replace one row by a row plus the multiple of a different row, you end up sort of sliding the region. You don't end up distorting the area. And so the determinant, the absolute value of the determinant, behaves exactly like the area function or the volume function. And when you have the identity matrix, the area is 1 or the volume is 1, and the absolute value of the determinant is 1. So the volume function or area function behaves exactly like the absolute value of the determinant function. And since those properties that I was mentioning characterize a function, there's only one function that does those things, that behaves that way with row operations and scaling multiples. Since they do the same thing, and there's only one function that does that, they must be equal. That's the intuitive idea of why the absolute value of the determinant of A has this volume interpretation. Because they do the same thing, they behave the same way with the elementary row operations, and since there's only one function that behaves that way, they must be the same. Okay, so I just wanted to explain this because this fact is used, this fact that the absolute value of the determinant is like a area or volume scaling factor. The area is like a two-dimensional volume, right? So there's like one-dimensional volume is like length, two-dimensional volume is like area, and then there's three-dimensional volume, and then you have more generally an n-dimensional volume. So that would be for n by n matrices. And this fact is used in multivariable calculus when you're doing integration. So if you take multivariable calculus and do double integrals or triple integrals, you have to use something called the change of variables formula. And in the change of variables formula, there's the absolute value of the determinant of a certain matrix. The matrix is called the Jacobian. And the reason why that's there basically is because you need to adjust for the fact that what the Jacobian matrix is doing is it's changing the areas of the regions in R3 or R2. Okay, well, it's okay if you didn't understand that. The point is that this fact is used in multivariable calculus. Okay, thanks for watching.